have Tom Stiadle, everybody's going to speak. We'll have 35 minutes total. Up to you to speak for 30 or leave 5, or speak for 25 and leave 10. So we're going to go to 35 minutes total for each speaker here. We have Tom Stiadle about dynamics and perception. So take it away.
Hi. So I'm literally last minute, well, maybe not literally last, replacement, no, stand-in. I've got asked, and I threw something together, yesterday afternoon pretty much, and early this morning. So I'm lowering your expectations. But it was supposed to be about, heat and all that. And I'm actually not going to talk about heat, although I do have a heat talk. But I thought I'd do dynamics, though. And perception, and I'll try to remember to say when I'm talking about perception, because we don't think about that. We all have our techniques, differential equations or various other things, but we get seduced by them sometimes. So I'm going to point them out, I hope, at least a little bit of that. So anyway, a little bit. I'm drinking decaf, so hopefully I won't go too fast, but if I do, you stop me. So, and there's always that tension between, am I going to get done too early or too late? Anyway, so relevant, what's climate? And everybody knows the little joke about climate is what to expect and weather is what you get. And that's part of this perception thing, right? It's true, that little catchy phrase, but we tend to think that climate is permanent. And that's because we know what it was like in our lifetime, but it changes, even in our lifetimes. But when it changes, we think that because when we were growing up in the 1970s, or however old you are, when sometimes we had snow on Easter, which granted Easter moves around, but okay. We think that that's like a normal thing, and then when it doesn't happen, we think that stuff has changed. But we don't really know, right? But everything changes, so you should take calculus. I don't know if, I don't think he said, my title is Professor of Mathematics, so, okay. But it's all related, right? But change is a funny thing, and most people don't think about it. When change happens, it doesn't just happen instantly. Even when you flick the light switch, which now with everything's fluorescent, it still doesn't happen instantly, but it used to be with incandescent bulbs, you thought it happened instantly, right? But it just happened so fast you didn't notice it. That's a perception thing. In psychology, they call that threshold. In industry, they call it tolerance, right? But everything happens at a rate, and we care about rates because rates add up, and that's the whole calculus part. So there's probably going to be stories that I'll just tell as they come to my mind, like they are right now. My father has no sense of engineering or mechanics or anything, so he really thinks that when you pull the plug on the drain, the water just instantly goes out. But we all know it doesn't. It happens at a rate. So we need to take those things into account for everything, including if you're going to try to model climate or model anything else. So anyway, my example, because I wanted to, since you're here in Aurora and people are probably from all sorts of places, I thought I'd use some local stuff, so I would talk about, or I would mention ice ages. And I don't know if CK is an official abbreviation, but I mean 100,000 years. Is there an abbreviation for 100,000? There probably is. But okay, I'm going to go with CK. All right, but they're not random. Things happen for reasons, we hope. Otherwise, we wouldn't be trying to do science. And so there are astronomical, geographical, or geological reasons that things happen. And there are other causes as well, since this is the biophysical economics group. Biology makes climate happen. They're like us, but not just us, everybody. Bacteria, insects, real players. So, anyway, but there are patterns. And ice ages that we recognize mostly happen in the northern hemisphere. There are various reasons for that, but the biggest reason is, somebody want to say? That's where the land is, yeah. So when they make the maps, and everybody wants to get politically correct and say you should make your map the other way around with the southern hemisphere on the top, well, yeah, there's probably some prejudice involved in having the northern hemisphere on top, but a practical reason is that's where all the land is, or most of the land is. Anyway, but yeah, that's where the land is, and that's where ice can form, because ice doesn't like to live on the ocean. It's really hard to make the ocean freeze. It can, and you can do little experiments in a water glass with your kids with ice cubes that are made with food coloring and everything, and do little experiments. But basically, ice doesn't want to form on the ocean. So, but it has consequences, and I wrote there, I think, yeah, look outside. Well, don't do it now, because in most of the buildings on the campus, if I'm teaching a class and I'll say that, look out the window, you can look out the window, and or go next to the next door and look out the window, and you see the Finger Lakes, or at least one of them. There are consequences. Right? I said there are consequences of climate, and that's a big one. So I think I have a picture of the next one. Well, okay, there's more consequences, more patterns. I read recently that, so we all know, this is pretty old, that North America is rising because it's still recovering from being covered with ice. But I read a few weeks ago that it's sliding south, and not because of plate tectonic activity, which we all believe in, but it's sliding south because of recovering from being held down apparently by ice. Interesting. And when whoever said it, when land moves, the climate moves too. So it's consequential. Oh, there's my picture. Okay, Great Lakes. Those are caused by ice ages, glaciation. And if you drive an hour and a half north, you'll run into Lake Ontario. And if you go a little bit west, you run into all the rest of them. Oh, that's too far ahead. Yeah. Okay, you run into all the rest of them that are bigger, but they're consequences of climate. And then locally, they influence our weather. We get a lot of snow, depending, and a lot of it, most of it comes off of. For us, it's mostly there it is. For us, it's mostly from Lake Ontario because we're around here someplace. But the Finger Lakes, when you look out the window, that's one of the bigger ones, one of the two largest. We actually get snow off of the Finger Lakes, which some people don't know, even who live here. Some mornings in the winter, especially if it's really cold, you'll go out and it'll be a blue sky like today, and it'll be snowing. Not like snowing, but it'll be like little flakes coming out. And those are lake effect from the Finger Lakes, which are right next door. Probably not down here in Aurora, but if you go up the hill, because it has to rise up and then fall down. If you go up the hill at my house, you'll have a little bit of snow in the morning, and it's in the clear blue sky. It's like rain in Hawaii with the clear blue sky. And that's a consequence of glaciation, which is a consequence of climate and changes in climate. Again, things coming to my head. One of the things I point out to students sometimes in the morning, because I usually teach at 8, I'll take them outside and say, look at the lake, look up. And yeah, we'll look up and say, yeah. well, there's a lake, yeah, I know. But look up, and if you look up and look along, there's a whole cloud that goes the length of the lake. Go ahead, just talk. Oh, yeah, you don't raise your hand, you just talk.
Oh,
I'm not backing.
when it snows at your house, can you look across the lake and see if it snowed on
Yes.
that side too?
Yeah,
Does it?
not as much.
Not as much.
No, but there's another lake. Okay, so here's us. There's another lake right over, or right to the west. So they're getting snow here. A little bit of it comes over here, but not as much. I mean, it dies off, right? So, but yeah, we're right around here, right at this curve, and just up the hill. That's where it snows. But they get it over here too. But you know, by the time it gets over to the west side, or the east side of them, it doesn't. You can see it if you look really hard. It kind of you have to like know it's there, and then you see it, that kind of thing. That's a good question. Where was I? Snow and the lake. I don't know.
Glaciation.
All right. What was it?
The lake is caused by glaciation, and then the lake causes flood. I mean,
It's feedback, right? Feedback. Yeah, that's one of the words we all use. Here's some. So that influences our weather. The fact that those things are there, and the Ohio Valley. I grew up in central Pennsylvania. That influences their weather because storms tend to track along this line, right? So our storms for winter tend to go this way. Not the storms, but most of our daily stuff goes this way. Storms are bigger, you know, they follow the continent. But in central Pennsylvania, they tend to follow this thing. But the Ohio Valley is also, that's where glaciers end, right? So if you've ever driven through Ohio, in southern Ohio, it's pretty flat. And then you cross the Ohio River into Kentucky, and it's not mountains like we don't really have mountains, but it's not like the Appalachians anymore, but it's bumpier. And that's because the glaciers ended at what's now the Ohio River. So anyway, stuff happens. So there's a picture of a glacier. Yeah, you can still see a few. But that's glaciation. That's a whole different story. And come on. Okay. So here's the Ohio Valley. Great. Okay, so it has consequences, but it's usually not an immediate thing. And as I mentioned before, we sometimes think it's an immediate thing, and sometimes it probably is, but we don't know. And we'll talk about that in a little bit here. But that's where the thing about, you know, weather versus climate. Weather is what happens today. Climate is what you think is going to happen over the broad term. But, you know, but if we're doing science, we have to measure stuff. And we do that all the time, but we really don't know at any given moment. We always have to be skeptical, and we like to think that we're certain, but we're supposed to be smart enough to know that we're not certain. So, all right. What comes next? Oh, I like this one. So things that are changing that we can know about and think we know about, but I said at the beginning in the title, perception. Here's a perception thing. So let's see. Sorry, I can't reach. I don't want to end this show. How do I minimize this, Dana? All right, I'll end and start again. Oh, there we go. Okay. I want this. You've probably all seen this, but I really like it, so we're going to do it. Is the sound enough?
Mm-hmm.
Okay.
student. Candidate in art.
Despite a lifetime of the very best education, students in our classrooms are failing to learn science. Many of these students will graduate from college with the same scientific misconceptions that they had on entering grade school.
Can you turn it up?
That's how a lifetime of education affects our understanding of science. We asked these recent graduates some simple questions in astronomy. Consider, for example, that the causes of the seasons is a topic taught in every standard curriculum.
Okay, I think the seasons happen because as the Earth travels around the sun, it gets nearer to the sun, which produces warmer weather, and gets farther away, which produces colder weather, and then hence the seasons.
How hot it is or how cold it is at any given time of the year has to do with the closeness of the Earth to the sun during the seasonal periods.
The Earth goes around the sun, and it gets hotter when we get closer to the sun, and it gets colder when we get further away.
These graduates, like many of us, think of the Earth's orbit as a highly exaggerated ellipse. Even though the Earth's orbit is very nearly circular, with distance producing virtually no effect on the seasons, we carry with us the strong, incorrect belief that change in distance is responsible for the seasons.
Oh, that's the end of that. I show that in a lot of my introductory classes that have nothing to do with whatever the class is about. I like it because, for two reasons. First of all, I can say, be glad you came here and took my class instead of going to Harvard. Because then you would end up, working for some Wall Street firm. I don't know. Oh, there we are. So that's a little joke, the loser Harvard grads. But did anybody go to Harvard who wants to admit it now? Probably somebody. But, okay. Anyway, but the point is perception. You get these ideas in your head and you think that that's like reality, but maybe not. And maybe the reality that you actually measured in all earnestness and goodness, maybe next year you'll find out there's something else, right? So, and we don't get uptight about that. That's another one of my teaching themes. We don't get uptight about that. We just say, okay, well, I have new information, so all right, let's move along. So yeah, what causes the perception? I already said all that stuff, I think. But it's about stuff that's changing very slowly, like over the course of a year, which when you're 2 is a long time. But stuff does change. You just don't see it really quickly. That's that threshold perception thing I was talking about. But it does have an effect over time, and it's measurable. And another one of my little stories about the seasons, if you actually get out a calendar, which at my house, not in my office anymore, but at my house I actually have a physical calendar, right? You flip over. If you count the days, you can look and find where it says first day of spring and find where it says the first day of fall, right? So vernal and autumnal equinoxes. You can count the days between them. Actually, do this. And I make kids do that, and they say, what? But if you count the days, and if you decide that the year is really 2 seasons, there's one called summer and there's one called winter. If you count the days, you find out that the summer is in the northern hemisphere. The summer is longer than winter by about 2 or 3 days. So like countable. It's not like, a few seconds here and there where you need GPS and all that. It's, and the ancients knew that. They really cared about the calendar more than I do. I just need to know when I have a meeting and whether I should skip it. But they knew that, and they could count it, but it never occurred to them. First of all, that the Earth was going around the sun, although people kind of knew that at various times, 2,000 years ago. But even then, everything was supposed to be a circle. But then, if that's true, why is summer longer than winter? And the reason is it's not a circle. But anyway, what's that?
Oh, not a circle.
It's not a circle. Yeah, did I say it wrong? It's not a circle.
It's not even ellipse.
Yeah, it's not a, well, You could guess that it's not a circle, but it wasn't considered a possibility until Kepler. And he was finally convinced by the data. He didn't want to believe it either, but he was convinced.
Because God is perfect and makes things in circles.
Yeah, and that's the hell of it is, every orbit has to be a conic section. So a line, lines never happen. A point, points never happen. A circle, circles never happen because they're perfect. But ellipses happen, and it's a good thing because if you had to be a circle, and then any little thing went by, like a tiny meteorite or meteoroid, it would disturb your orbit, and you wouldn't be a circle anymore, and you would fly off into the galaxy or you'd fly into the sun. But it's a good thing that doesn't happen. That ellipses are allowed because it gets perturbed, but it's still an ellipse. Okay. God is perfect. Well, apparently because he let ellipses happen. You can read that. Okay, other things that we use. Statistics. We like statistics. You just have to be careful. And you always give this little speech to your students about there's correlation is not the same as causality. Go talk.
5 minutes.
Really? I thought it started at 5:00.
Well, it'll go to 9:30 for 35 minutes.
Schedule says you started at 8:45.
No, I did not. All right, well, okay. We'll skip ahead. All right, when you have large numbers, talk to me afterward about lines in Plato and Bears. It's actually a good blog. But be careful about causality versus correlation, and correlation versus relation. They're different, right? Correlation is linear, relation is anything. Who knows? One of my favorite examples is if you want to look at temperature change, it's really nice to look at biological examples like, where different things grow, where they used to or where they don't anymore, because those are millions of data points, hundreds of millions of data points. And that's better than, I measured the temperature over the last 50 years. Well, I don't know. Could be lots of stuff happening, right? Could be a long-term pattern. Could it just be, the last 50 years? I don't know. But I like that one for that reason. So let's skip ahead since she's hurrying me along. We like to do models, and you hope you're getting real results. But here's a model, and you want to look at the thing on the bottom. There's a probability density, when you're going to have something happen. And then this thing is over time. Because it's probability, I scaled it all to be between 0 and 1, because that's how you do probability, right? And at the end of time, you want it to be 1. Okay, that looks good. This one kind of has the same general shape, different formula, same general shape, but it goes from 0 down here at the end to 1 at the other end. That's good. And then here's everybody's favorite, which is Gaussian, or normal distribution. And I didn't have an earth function on my graphing facility, but if you graph the total, it does that same general shape. So talking about when we're measuring over 50 years or whatever, we kind of see the same sort of picture, and at first glance they are qualitatively the same, right? Here it looks like a bell curve. Here it looks like a bell curve kind of spread out. Here it looks like a bell curve. All look sort of the same, but they're really different. And they're not just quantitatively different, because, they're quantitatively similar, that they go from 0 to 1, but they're qualitatively different too, even though it looks like they're qualitatively the same. And so you have to be careful about stuff like that. And this last one, I think, the first one, it's called a Lorentz distribution, Lorentz density. Turns out it has infinite standard deviation. Although if you look on Wikipedia, it says it's undefined, but it's infinite. So just trying to hurry along here. Quality influences quantity. And that's why we have to be careful about looking at small term stuff, because you might think it's one thing, but it might be something else. So, all right, let's write that. so I can finish up in the 5 minutes. Let's really rush ahead. Trying to solve things, again, I was trying to go through different stuff that we use. We use differential equations, we use statistics. Another thing we use that might not be so commonly known is something called dynamic programming. Has anybody heard of that? You people? Yeah, okay. What it really means is, it means my wife is really smart. And when her sister's 10 years older, and when her sister was in college, she had a friend who was a psychology major who needed to give IQ tests to younger kids. So my wife got volunteered, and she was doing the IQ test, and one of the things was to do a maze. And how do you do a maze?
Start at the end.
Start at the end. So that's what she did. And this woman yelled at her, "No, you can't do that." "Well, why not? You said do the maze." "Well, yeah, but you're not supposed to start at the end." "Well, but that's how I do these." And so this student had to go to a professor and say, "Is that okay?" And the professor said no. But what's funny is, well, she was actually showing that she was smarter than the maze by starting at the end. That's what dynamic programming really is. It works for lots of stuff, like solving science problems. Start at the end, you're not cheating, or if you are cheating, cheating is the thing you should do. You start at the end and work backwards. And it works with all sorts of stuff, and I wrote down tic-tac-toe, oh, mazes, yeah, tic-tac-toe, pick up sticks, that game. I think it works with blackjack. It works with lots of stuff.
Bayesian statistics.
Yeah, yeah, you're just going backwards, but you can solve problems easier if you do that. And that's mostly what we actually do. We like to think in the Platonic sense that we're starting, from a mathematician point of view, starting at the beginning, and here are my rules, my axioms, and I do whatever. But that's not really what we do. We do this. So anyway, good ones are complicated. So anyway, just to finish up, to rush through, sorry. Are there any questions anybody wants to ask, or you can ask me later, or I can give you the URL for the lions and Plato and bears.
I think we definitely have 5 minutes for questions, so if people have questions.